Let C be the circle centered at 0 with radius 2, traversed counterclockwise. And we want to compute the contour integral around this circle of e to the z over z squared minus 1 dz. Now this function has singularities when the denominator is 0. Z squared minus 1 equals 0 gives z equals plus or minus 1. So there are two singularities at plus 1 and minus 1. Both of these numbers are inside of the circle, centered at 0 with radius 2. So we have two singularities inside the circle. And so to compute this integral, we're going to use a combination of the extended deformation of contour theorem and Cauchy's integral formula. Cauchy's integral formula. So we're going to use these two things. So first, the extended deformation of contour theorem says that if we have some contour, positively oriented, simple closed curve, we'll call that one C. And if we have a few other curves inside of it, simple closed curves C1, C2, C3, C4, then as long as the integrand is analytic on all of the curves, so on C, on the boundary of C, on C1, C2, C3, and C4, etc., and in the region in between them, so if the function is analytic in all of those places. So in other words, we're isolating the singularities to be inside of these circles. That's how we use it. So the function that we're integrating is analytic everywhere on the curves and in the region in between them. Then the integral around C of the function is equal to the integral around C1 plus the integral around C2, etc. So the way I've drawn it here, there's a C3 and a C4. So the deformation of contour theorem would just have one circle inside. The extended deformation of contour theorem has some whole number of circles inside. I drew 4 in my example here. And then Cauchy's integral formula says that the integral around a simple closed curve of an analytic function divided by z minus z0 to the n plus 1 dz, where z0 is inside of the simple closed curve, is equal to 2 pi I divided by n factorial times the nth derivative at z0. So we're going to use these two facts in conjunction. So we're going to have two integrals because we're going to use two circles, one around 1 and one around negative 1. So we're going to have an integral around that goes around 1, where the circle goes around 1, and then another integral where the circle goes around negative 1. And for each of those integrals, we're going to use this formula. So the first thing we're going to do is we're going to write our function e to the z over z squared minus 1 as e to the z over the z minus 1 times z plus 1, just simply factoring the denominator. And now our circle, original circle, centered at the origin, has a radius of 2. So here's the number 1. We're going to take a small circle around the number 1, and we'll call that C1. So C1 is some circle centered at 1 with a small radius. Maybe R is half. That'll work. And we're gonna, here's the number negative 1. We'll take another circle here, C2, and C2 will be a circle around negative 1. So that's a circle center negative 1 with same radius will work. Some small radius r, 1/2 will work for both of those. So now this function is analytic everywhere in the plane except at -1 and 1. So it is analytic on the curves and in the region in between the curves. The singularities are inside the circles, the small circles. Okay, so let's calculate the integral around C1 of e to the z over z minus 1 times z plus 1 dz using Cauchy's integral formula. So the number 1 is inside, so the Cauchy's integral formula has z minus z0 here, where z0 is a point inside of the simple closed curve. So 1 is inside of the simple closed curve. So this is going to be our z minus z0. So z0 is 1. Then the power on this factor is 1, and in the formula it's n plus 1. So n plus 1 is 1, so n is 0. And the function f of z is everything in the integrand other than this z minus z0 to the n plus 1. So everything in the integrand except for this factor. So f of z is e to the z over z plus 1. E to the z over z plus 1. This function is analytic everywhere except at -1, and so it is analytic on this curve C1 here and inside it. So Cauchy's integral formula says that this integral is equal to 2 pi I divided by n factorial, which is 0 factorial, which is 1, times the 0th derivative, because our n is 0. So f of 1, our z0 is 1, f of 1. So the answer to this first integral is 2 pi I times f of 1, which is e to the 1 divided by 2. So e over 2. So this integral is equal to e pi I. Now we'll calculate the integral around C2, and the deformation of contour theorem says that we will add those two together. So around C2, e to the z over z minus 1 times z plus 1 dz. Now the circle C2 has the number -1 in its center, and that's going to be our z0. So z0 in this case is -1. The power on here is the same as there. It's 1, so n is 0 again. And in this case, the f of z is everything except the z plus 1 factor. So e to the z over z minus 1. So this integral is equal to 2 pi I divided by 0 factorial times f of -1. So this is 2 pi I divided by 1 times f of -1 is e to the -1 divided by -2. So this is negative pi I over e. The 2's cancel. The e comes to the bottom, and we have a negative. So the final answer to the integral is to sum these two, e pi I minus pi I over e. So the integral of the function e to the z over z squared minus 1 dz, where this circle was center at 0, radius 2, it's equal to e pi I minus pi I over e, or pi I times e minus 1 over e.